Good afternoon, everyone. Welcome to the evening sessions, and we start with Kegan, and he's talking about unable to decrypt this message. The stage is yours.
Thank you very much. Hello, everyone. Thank you. Hi, everyone. I'm Kegan. I'm one of the original developers who created Matrix, and I would like to spend some time going over why Matrix has some issues. We've been unable to decrypt some messages, which I'll refer to as UTDs from here on out, what we're doing about it, and the kind of progress we've made in reducing UTDs across the ecosystem. And then we'll dive a little bit deeper into the anatomy of a UTD bug and look at a new testing framework which I've developed to try to improve reliability across the ecosystem. So first of all, what do UTDs even look like? So here's it's the butt of jokes for many people. UTDs are basically error messages that are displayed to the user every time they receive a message that they can't decrypt. And the text can vary on different clients, so it could be waiting for this message instead. But either way, the end result is the same, that you can't read what someone wrote to you. So how does this happen? So when you send a message, the message is sent in two parts, effectively. You type your message, your phone will break up this message into an encrypted payload, as well as the decryption key. The idea here is that the encrypted payload heads over to the other device, and at this point, it would be you'll be unable to decrypt this message, right? Because you need the key in order to go and decrypt that message. And then for whatever reason, this key has an issue getting all the way to the other side. And there could be many, many reasons, which we'll go through, but this is the ultimate reason of why you're unable to decrypt your message. So if you do manage to get things on both the key and the encrypted payload on the other side, you'll obviously be able to use that to decrypt the original message. So why does this happen? There's a few reasons for this. So on the server side, you have software reliability issues. So there are bugs. We fix the bugs. People don't upgrade to the latest versions. It causes problems. There are hardware reliability issues. So this is basically anything which can corrupt your database. So if you disk fill, if you don't do backups and you have to roll back, anything which can cause timeouts can also cause issues. So if you are running it on an underpowered machine, then it's going to take a long time to process those requests, and eventually maybe the other side will give up, and they will not be able to send the key across to the other side. There are network reliability issues as well. So if you think most people here probably run their own server, if you're running this on a Raspberry Pi, how many nines of uptime do you have? You might have 99% uptime versus someone like WhatsApp who will have easy 5 nines of uptime. So if your server is down, obviously the keys can't make their way across to the other side. There's also server diversity issues. So on this example, you can choose any row, any server. You can run any server. You can then choose any reverse proxy on top of that, and then you can choose any extension. Sorry, let's get my HDMI. You can then choose any kind of extensions on top of that. So I don't know why this is having issues. So I've mentioned sliding sync here, but that's only because sliding sync obviously affects how data is sent from A to B, so it can affect whether or not the key gets delivered. On the client side, there are a few issues that can go wrong here. So again, you have the same thing. There are bugs on clients, and people don't upgrade their clients, or they've forked an SDK, and then they don't keep that fork up to date with the latest upstream. There are robustness issues. Clients need to work with a wide range of servers, which are on different versions. And also, you need to validate the network traffic that's coming off. And this ultimately increases complexity for clients. And things can go wrong if you aren't looking at the right keys, or if you're only looking at the newer version and not looking at the older version, and things like that. There's also issues with client diversity. So here are some clients, and you can read this in a vertical way. Each column shows the crypto and SDK dependencies for some clients. And there's quite a big variation here, right? So people are generally using the one of two cryptographic libraries, but the SDK level there's loads of different varieties here. And this will become important. This big variation means that there's ultimately more code that's in the ecosystem, which means there's more chances for bugs. So at a protocol level, this happens for a number of reasons. Some of it is because there are unbounded group sizes. So WhatsApp set limits. So 1,024 members in a group chat is the maximum with 4 devices per member. Signal has 1,000 users with 5 devices per user. We don't set any limits. There are end-to-end group chats in matrix.org, which have got 1,500 members, right? I mean, these communities can't exist on other networks. And this matters, right? Because the more devices that you have, the more chances things can go wrong. You have to send keys to more users. If you don't manage to send the key, you're going to get a UTD. There's more data to transmit. So, if you are running an underpowered server, then you're going to need to service all this. You're going to need to process all these requests. And if you aren't able to process it in time, there's timeouts, and this is going to also cause UTDs. And it also increases the chance that you need to cycle the room key. So things like if you log out of a device, everybody else needs to say, okay, well, I'm going to generate a new key now to make sure that the device that logged out isn't going to be able to decrypt these messages. And so if you have many devices in a room, there's going to be more opportunities for people to log out as opposed to having fewer devices. On a federation side, this is really just a general concept here because federation adds an entirely new way that things can go wrong that things like WhatsApp and Signal just don't have. It's an entire new section, a new class of bugs which can happen. For backwards compatibility and ecosystem inertia, this is kind of hand in hand. So when the protocol upgrades, we obviously need to be backwards compatible with what happened before until the ecosystem has upgraded sufficiently, and that can take a long time. And during this process, you might be having to maintain both versions of the protocol, or you might have issues where you are having to migrate people across, and this causes problems. So again, if you are WhatsApp or your Signal, you can kind of increase your client and your server in lockstep. You control the client, you control the server. Your server can just be like, okay, if you're on version 2, you have to upgrade. You just can't send messages otherwise. We don't have that luxury in Matrix. The ways that we're trying to fix this is obviously identify bugs in clients, in the servers, in the protocol, and there is a canonical issue up there which you can go to, which gives you a big old list of GitHub issues. We're trying to reduce complexity, at least on the element apps, by kind of deciding on one code base for element apps and then using that. So the idea is that we fix a bug in one place and one place only. We don't have these issues with having to make sure that, okay, fix the bug n times, make sure these SDKs are all up to date. And for element, we're converging on Vidozamats for the crypto library and Matrix Rust SDK for the SDK layer. There are protocol changes that we have proposed. This is mostly around federation reliability. So when federation is unreliable, are there ways that we can make it so even though you can't talk to this other server, it's okay, you can still be able to encrypt successfully for the other side. We're also adding end-to-end regression tests. So this is a new tool which I'll talk about a bit later on, and we are tracking progress. So on the element apps, if you choose to opt into analytics, whenever you see a UTD, we get notified about this, and therefore we can actually see, at least across element apps, what percentage of people are seeing UTDs. So is all of this kind of stuff working? And using those things, we can see that, yes, it is. So this plots the percentage of users who observe a UTD on a given day across element apps, and from the beginning of April through to, I think it's the beginning of June. And you can see that this has decreased quite significantly. It currently is tracking about 3% on web, 4% on iOS, and 6% on Android. Ideally, this would be even lower, obviously. And again, if you're a part of a large group chat and you send a message, if that message has failed to encrypt for a large percentage of the users in that room, and that room has 1,000 users, then that'll be shown up in here as a spike of UTDs. So one failure here can be magnified in this graph. A slightly more recent graph here from, I think it's the beginning of June to the beginning of September. You can see how this is also going to continue to decline, and we've also got more stabilization. There's less variability in the actual graphs, which is a good sign that the overall apps are becoming more stable. So this graph is not plotting element-to-element messages. So this really matters because if you have a perfect client and a perfect server, but the sender is not on a perfect client or perfect server. The sender can just fail to encrypt the room key correctly. And if they do that, then no matter how perfect your server and client is, you will see a UTD, because the problem's not with the receiver, it's with the sender. So this is why, again, we need to bring the entire ecosystem along in this journey to make sure that UTDs can be fixed for everyone. And overall, though, like, we've made some significant improvements. So we've roughly halved the UTD rates across all the Element apps in about 5 months. So with that kind of trajectory, we know there are improvements to do on this as well, and there's several more. So this graph should improve even more in the coming months. But like, this is the kind of stuff that we've been working on. So that kind of ends the high-level summary of like what we're doing and the progress we've made. And I'm going to dig deeper technically now onto the underlying causes of UTDs. I'm not going to touch on every possible failure mode, but I will be touching on like the most common failure modes, and I will reference real GitHub issues where they are appropriate. So a little bit of background. If you went to Sumner's talk and you understood stuff like that, then this is dead easy for you. But at the very basic level, you need to understand a little bit about public key cryptography, specifically encryption and decryption, which is a program can generate a public-private key pair. And these are mathematically linked to each other, and you can send the public key to anyone you like, and they can then use that public key to encrypt some data for you, for the person who generated that key. They will then send you this encrypted data, and then that private key can be used to decrypt that data, and it must remain secret, it must remain only private to you. There are other techniques that you can do with public key cryptography, which Matrix does use, like signing and key exchanges, and Sumner's talk goes into a lot of detail with that, but you actually don't need to understand this for the purposes of this talk. So at a more technical level, how are we defining what a UTD is? So there's kind of two tracks here. So if the message was sent before you logged in, then the sender's not going to have encrypted for your device because you weren't logged in. Right? That's a reasonable thing. This is what we are calling kind of expected UTDs. We don't expect the sender to have encrypted for your device. If you happen to have another device that was logged in, then you may be able to use key backup, which Sumner covered, and you may be able to get the key for that message via key backup. But otherwise, if you're not using key backup, it's just you're not able to read that message for a good reason, because the sender never sent you the key. However, if the message was sent after you logged in, then the sender should have encrypted it for your device. And if they didn't encrypt it for your device, that's a problem. Now, it may just be that the key is in transit and it will arrive if you just wait a while. But alternatively, it may be permanently undecryptable. And that is how we're defining that to us is what a UTD is. So you can think of crypto in Matrix for this particular kind of a thing where events sent after you've been logged in as like a 3-layer stack. At the base layer, you've got, ultimately, you're sending data from A to B. This is using the HTTP APIs that are in the spec. And then built on top of that, you have Ulm, which is a way of establishing a secure channel between two devices. It's a point-to-point. This is the double ratchet algorithm. It's point-to-point encryption only between two devices. And then built on top of Ulm is Megolm, which is used to establish a secure channel for multiple devices. So it's worth noting here as well, if you happen to be in a DM and that DM there's only two devices in the room, because I only have one device and the person I'm talking to only has one device, you're still using Megolm, right? Just because there's only two devices, we still use the full stack regardless of the membership lists in the room or the devices in the room, the number of devices in the room. So another way of representing this is to look at an HTTP dump. So here are some HTTP requests. And you can see the ones I've highlighted in that kind of yellowy orange is that base layer. These are the HTTP APIs that have been made that are relevant to encryption. And you see the first 3 requests are all to do with Ulm. This is all to do with establishing that secure point-to-point secure link. And then after you've done that, you can then do the Megolm stuff. And this is another way of thinking about this problem. A final way of thinking about this is a very oversimplified kind of data model here, whereby if you have a device, your device is going to generate a bunch of keys. The important keys here are device keys and one-time keys. Device keys are long-lived identifiers for the device, and then one-time keys are hopefully made obvious by the name. They're used once and then never again. So in order to communicate with someone, you need both these things. You need the device key and you need a one-time key. Because device keys are long-lived, they're not very often the causes of UTDs. One-time keys, though, are, because they need to be constantly cycled. They can get used up, and they need to be replenished on the server as well as on the client. And we'll talk more about how this can fail. So in the happy case, what happens? You have a home server, and then you log in on a new device, and your device is going to generate a bunch of keys. It's going to keep the private parts private. It's going to upload the public parts to the home server, and then someone else is going to do the same thing. Now, these two devices are unaware of each other until there is some sort of reason for them to be aware of each other. So maybe the blue device has joined the same room as the green device, or maybe they were in the same room, but you've just logged in on a new device, so it's a deviceless update. Either way, they become aware of each other. What happens is the same regardless. There is a request to the server to fetch the other device's device keys, and that's it. So now they become aware of each other. If the blue device wants to send a message to the green device, they need a one-time key for the green device. So they will go and request a one-time key from the server, and then they will use the device key and the one-time key to create those two messages we spoke about right at the beginning, one of which will be the key, which they'll send up to the server, and then one of which will be the encrypted payload, which they will also send up to the server. Both of those messages need to make it to the other side, and they can then be combined to get the actual plain text. So what can go wrong in this model? So the first thing that can happen is that you fail to upload the one-time keys for whatever reason. Maybe you are on bad network data or something like that, and you're just not able to upload those messages. Or maybe because you did upload messages, so you did upload one-time keys, but then all those keys got used up, and your device has been offline for 6 months, and they just haven't been replenished. So we fixed this using fallback keys. We had to add in a whole new concept to address this because, of course, people may be using devices that are not online for a long time. Alternatively, the one-time keys may be uploaded. Okay, so there are one-time keys that can be delivered to whenever you want to send a message, whenever you want to encrypt a message for the other side. But for whatever reason, the request to claim a one-time key, to obtain one, that doesn't work. Because what happens here is the device is going to be generating a request that's going to go to their home server over federation to the other side to say, please give me a one-time key. And then that one-time key needs to be sent back to the client. And of course, these are all links that can fail. It can fail on the upload, it can fail over federation, the other side, it can fail at the recipient side. And what happens for the federation failure is, we can do some improvements to the protocol here to try to make this a little bit better. So you can do things like you can eagerly share fallback keys in this example. So even if the other home server was not available, you'll still be able to obtain at least some sort of key that you can use to encrypt messages for the other side. These are real issues that we've had, there are GitHub issues related to this. So another thing that can happen is that one-time keys can get out of sync. So what this means is, so if you remember, the device is generating public-private key pairs for one-time keys. It's uploading the public parts. It's keeping the private parts private. And then Sumner alluded to this, and it is a real problem that client databases, they can forget things. So in this scenario, say the device forgets the red key. Now, the device may realize, okay, I don't have enough one-time keys. It might decide to upload more one-time keys or something like that. But important thing here is that the home server's got the red key. The device does not have the red key. So what happens if that red key is used to encrypt the message for the other side? Well, you're not going to be able to decrypt it because you don't have the matching private part for that red one-time key. This is quite a big issue. There's a number of issues which are all related to this sort of thing. Some of them are to do with servers, some of them to do with clients, but these are many reasons that these things can get out of sync. Another way that things can get out of sync is with the membership and device lists. So in this example, Alice and Bob are in the same room. They both have one device. Everything is happy. Everything is working. And then Alice decides to log in on a new device. So Alice logs into a laptop. At this point, if Bob were to send a message to Alice, then Bob's device would not encrypt for the laptop because Bob is unaware that this laptop exists. So even though the other side is aware, the other side is aware, but Bob's server nor Bob's client are aware of this. So what actually you need to do is you need to wait for an update message to get to the other side, but it's actually worse than this. It's not good enough that the home server is now aware that this laptop is logged in. You actually, because it's end-to-end encryption, right? So you need to actually wait for Bob's device to be aware that Alice's laptop has logged in, and only then will you actually have synchronized the device list again, so you won't be sending messages that you're not able to decrypt. This is a pretty big cause of UTDs. Like, there, again, many different reasons. Some of them are related to the server, some of them related to the client, but this can cause lots of issues, particularly when you join rooms. You may see this sort of behavior. So a final thing that can go wrong, so everything I've covered up until now has been to do with Olm, for the record, right? There's only this really on Megolm. Megolm is, someone alluded to it, you send 2 device messages, and you may fail to send that 2 device message, right? So you may fail to make that request to your home server. There have been bugs to do with this. Maybe you did send it to the home server, but you failed to send it over Federation. Yeah, there's been bugs to do with that too. Or maybe the encrypted message jumps ahead and kind of reaches the other side before the key. Now, this is quite a unique scenario because if this happens, you will see a UTD. You don't have the key, but the key is still in transit. This is why we say if you wait for a while, you may be able to decrypt it, because if that key does arrive 30 seconds later, then congratulations, it's actually not a UTD, you're all fine. But of course, maybe that doesn't happen. And yes, there are also issues on the receiving side as well. But yes, ideally, both the key and the encrypted message will make it to the other side, and then everything is fine. So everything I've covered up until now have been kind of protocol-level-y issues with clients and servers. I'm going to focus entirely on the client now, because clients, the way that you develop clients, specifically SDKs, can cause bugs if you're not too careful, and those bugs will cause UTDs. So even if you've not really followed the old Megolm stuff, this is like an entirely separate thing. So one thing that can happen is you can end up with a causality violation. So imagine you're a bot. You're using an SDK, and you say, invite someone to the room, and then you immediately send a message to that room. Most SDKs will fail to encrypt for the invited user's devices, and that will cause a UTD. And the reason why this typically happens is because when you send a message, they are loading the device, loading the member list of who's in the room from their database, reasonable thing to do, and then they're using that to map it to a set of devices and then encrypting for each of those devices. This is all reasonable things to do. But unfortunately, if you've invited a user and if they're waiting for the home server to say, okay, this person is now being invited to the room. And so there's this time period whereby if you haven't been told that this person's been invited to the room, then you're not going to be encrypting for that member. So this is entirely an SDK problem. It doesn't matter if you're using libOlm or vidosumats. This is entirely to do with the SDKs. This is why SDK development is quite hard to do correctly. You need your SDK to handle this. Rust SDK, for example, works around this by invalidating the membership list when you directly invite a user on that client. So it knows that, hang on, the membership list may be out of date. I should probably double check with the server before actually sending this message. Another thing that can go wrong is, we've talked a lot about big encrypted group chats with lots of people. And so as a result, there's a lot of data, a lot of keys. So maybe you need to batch some requests. This is referring to room keys. It could be one-time keys as well, doesn't matter. But ultimately, what happens if you only manage to send half of those keys? Then the other half of the devices are going to be unable to decrypt that message. So this is one of the biggest causes of UTDs for large group chats because of this batching process. And it's typically, again, when a new user joins an existing room and they're not able to actually claim one-time keys for all of the servers in the room. They can only do a partial subset. And again, the reason why they can't claim it from those servers is maybe because those servers are down. Maybe that's reasonable. But some of them could be just due to timeouts, right? If you are running an underpowered server and you need, like, yeah, please give me 100 one-time keys for the users on your server, and you're running it on a Raspberry Pi, maybe you can't service that request fast enough before the other end gives up. So this is why the hardware thing matters here as well. So either way, it results in the partial encryption of that message for users in the room. This has been seen in different SDKs. It's not unique to any particular SDK, and again, not unique to this endpoint to send to device or keys or claiming keys. It's also worth noting here that if the right answer to fix this is not to not send the event. If you choose not to send the event, then one dead server could just brick the room, right? Because then you'll never send any messages because you can't encrypt for every single device in the room. So what you really need to be doing is actually retrying these requests. And you need to remember these retries across restarts, right? Because it could take a while for you to send those keys. It gets really gnarly. And the final way that things can go wrong, this is alluding to issues that iOS quite uniquely has, because iOS, the client is split into two processes. You have a push notification process, and then you have the main process. And what happens if those two processes are not coordinating? If they're not coordinating and say there's some input that needs to be processed exactly once, but then each process processes it independently, you may end up corrupting some internal state in your database. This can happen, maybe not in exactly this way that I'm describing, but the general concept often happens. And to fix this, you do need to coordinate across multiple processes correctly. So some sort of cross-process lock typically is used. So hopefully I've kind of given the example, like given the impression that there's a whole wide range of things that can go wrong, and any one of these things can cause UTDs in different components. And how do you go about testing something like this? So looking back at hopefully a now familiar diagram, this is what Complement Crypto does. So it uses Complement, which is a test suite which ultimately runs home servers in Docker containers. And we reuse this functionality for Complement Crypto. But one of the key things it does is it also inserts a man-in-the-middle proxy. That means it can inspect client-server traffic, and it can not only just see were these requests made, it can also then interact and stop these requests. And it can stop it at both ends of the flow. So maybe you're uploading one-time keys, and I'll say, actually, no, don't send that to the server. Please return a HTTP 500 instead. You can test that. Or you can say, OK, yeah, let them upload the one-time keys, but then block the response. So this is where you need to make sure your requests are idempotent. So when it's all these sorts of things which you can now test in a reliable way. It also allows you to make HTTP dumps, so the dumps you've seen earlier. So if you're debugging tests and you want to know why your test isn't working, it generates HTTP dumps, which you can view in a web UI, which is all very nice. And you can also potentially do adversarial testing here. So you can say, OK, claim a one-time key, but actually don't get a key from Alice's device. Give it from Mallory's device or some other thing. So there's a lot of scope here for testing things. To test the robustness qualities, we also spin up clients in separate child processes. This means that we can actually go and send sig-kill commands to these child processes to see how they behave when you terminate them ungracefully. So this is the whole making sure that you do have a retry schedule that persists things to disk. Because otherwise, if it's all in memory, when you restart, you won't retry, and then you're not going to recover from being killed. And this matters, right? If you are on a PC and someone pulls out the cable, you don't get a graceful shutdown. You just die. Same with a phone, you run out of battery. It just goes, So you need to handle all of these sorts of situations. We've used Complement Crypto to detect numerous UTDs over the past 5 months. That's why we've seen so much progress. And it's also identified some CVEs as well, some vulnerabilities. So the main feature set I've kind of covered on most of these things here. The other thing it can do is combinatorial testing. It uses a single kind of API. It doesn't actually care if you're running JavaScript or Rust or something else. It's just so long as your SDK can meet this API, then you can use it. And this is a kind of example of tests that you can do. So this is just the happy case of does encryption work at all? It's only a couple lines of Go code. And it creates an encrypted room, joins the room, makes Alice and Bob start syncing. So this will also upload one-time keys and device keys. And then Alice sends a message, Bob waits for the message, makes sure that Bob can decrypt it. And you'll notice it doesn't refer to any particular client at all. And then when you run it in CI, it breaks that apart into lots of tests depending on how you've configured it. So you can test that like web is going to work with element X and vice versa, or element X clients are going to be able to talk to each other. And because it is just a Go test, you get nice things like it just works in your IDE. If you set your environment variables correctly, you can just hit run test and it'll just do the right thing. And then finally, there are more things that we can do to improve this so that there are more tests that we can add. And the main thing is we really do need to add additional SDKs. Hopefully, convinced you that we do need to bring everybody along in terms of improving reliability across the ecosystem, because only that way can we ensure that both the sender and receiver are functioning correctly. We do want to, I would like to thank BWI and other contributions of others for sponsoring this work, because they're sponsoring the future, not features. So it's really nice to see. Thank you very much.
Thank you very much, Kegan. And I think we have time for 1 or 2 questions only. Anyone?
Firstly, is the Rust crypto SDK or Vodosimac, are they also tested by this framework, or is it only Olm?
This framework is testing SDKs. SDKs choose which cryptographic libraries to use. So if Rust SDK only uses Vodosimac, so it's testing Vodosimac. But it's at a different API boundary. That's why I'm hesitating here, right? Because again, you could this also tests JS SDK. JS SDK, at least in the past, 6 months ago or however long ago, was using libOlms, in which case it would be testing libOlm. But nowadays it uses Vodosimac, so it can test both, if that kind of clarifies your question.
Yeah, it does. And let's say you have an Olm session, you have your outbound session, creates an inbound session on the other side. If your crypto device wipes all its sessions, which it currently does in the JS SDK rehydration, dehydration, or the other way around, is it not an issue that you have no more outbound or inbound sessions on one device and you still have lingering sessions on the other device?
That is going to be a more complicated answer, which I'll get you afterwards.
Yeah.
But yeah, I can talk to you about that.
Thanks a lot. And there was one more in the back.
When you have a net split between 2 servers and the server B has an invite and it joins a new user, and server A sends an encrypted message, do you consider that an UTD or not?
Good question. Good question. It would depend how state resolution would order those operations, right?
Well, the messages will probably arrive to the client in stream order, so because they will arrive later, they will be visible to the user.
Yeah.
It's not a UTD.
Yeah, I mean, you can argue the point, right?
The user won't be able to see
that
they're not supposed to see the message, but from the sender side, obviously that user shouldn't see that message. And there's no way to tell the user that this is okay.
I do think we did some work around this by decorating events with what was the membership of the syncing user at that time. So I think we do catch this. I mean, Rich will be able to clarify, but I'm fairly sure that we do catch this, and we display a different error message in that case. Yeah. Theoretical. Okay, fine. Okay. But yeah, we've thought about this because, yeah, state resolution then ends up, well with net splits, it becomes trickier to decide whether you should be able to decrypt or not.
Thank you.
Thank you all, and catch Kegan for more questions.